Hello and welcome to today's lecture. I hope last week you got the opportunity to do some examples in R. In last class we had solved few examples in R, showed you how you can create a vector, you can do basic scalar addition, subtraction and other operations, and how to do vector operations. So one of the things to remember is when you define two vectors and you are doing these operations get operated at an element wise level. In other words, if I define A as a vector which is 1, 2, 3, 4 and B as a vector which is 4, 5, 6, 8, then A star B will give me a vector which is 4, 10, 18 and 32, so on and so forth. So basically you have an element wise operation. A star B is operated at the element wise level and each product is given you as a separate vector. Okay. We had then shown that how you use the scan. So either you write A is equal to C of 1, 2 dot dot dot. So this is the syntax for entering number and concatenating them into a single vector, but of course this can be very laborious when you have big data. So and repeatedly entering next to each other can be a problem. So one of the ways around it is to use the function scan. So you can write data is equal to scan, and when you put no brackets when you enter, so you have the command prompt and where you can enter and these numbers get stored. Okay. Most important thing to note is in this case when you write the function scan, by default the software assumes that these numbers are real. So if I write Monday or Tuesday, then immediately this will give to an error. Okay. So the way around it is to write data is equal to scan and you have this additional term as what is equal to char. So then tell the software then knows that you are essentially entering characters while you are entering these. So then if you enter month, but when you enter you have to write it within quotes, Monday, Tuesday, Wednesday, so on and so forth. Okay. So and then it will automatically take it. You can easily add, so you have a vector A, you can add, let us say you can write A is equal to C of A comma 4, 5, 6, so on and so forth. So you can add these numbers either before or after the vector. So once you generate a vector, let us say you have a vector A is equal to 1, 2, 3, 4, 5, 6. Okay. You can use these essential functions like min of A, max of A, mean of A, median of A, variance of A and SD of A to get variance sigma square, sigma, this is just the median, you get x bar here and mean and max. Okay. So these functions will easily allow you to calculate numbers, particularly when these vectors are big or the numbers are big. Okay. Then we briefly discussed about plotting. Okay. So once you have a vector you can use, let us say, a box plot. So if you use like bar plot or bar plot of, let us say, xx or box plot of xx, yy, you will generate all these plots in the plotting function. So let us say I could have written box plot yy and then I could have written y lim is equal to C of 0 to 10. So this would have set the y axis range. So this is the y axis range from 0 to 10. So this is how I would have entered my y axis range to be between 0 and 10, so on and so forth. Okay. Histogram of xx or yy will give you the histogram or the frequency distribution, but it will also generate the plot. So just to get the frequency distribution you can write table of xx. Okay. So these are the basics. Now let us come to, so in the generic case you just do not have values, but you have values where there are more than one metric when chosen. Okay. So let us say in a class I want to correlate, so you have two vectors, you have chosen x and y. Okay. Of these x is, let us say, weight and y is agility, okay, or capability to run, let us say how agile or fitness, whatever you choose. Now logic would dictate, you would expect in general that if I were to plot x and y, if this is my x, this is my y, so x is my weight axis and y is my fitness axis. Let us say I normalize it with respect between a value between 0 and 10. Okay. So you would expect that as weight will drop, you can expect a curve like this, you can expect a curve like this, you can expect a curve like this, but it is highly unlikely that you will have a curve like this. This is highly unlikely from a physical point of view. So the object of this exercise is to correlate these two particular behavior, and this is how it is chosen in the principle of correlation. Okay. How are they correlated? So I can clearly see that in both, let us say this curve A, this curve B or this curve C, they are correlated. So as per this curve A, let us say they are saying that you see a strong correlation such that increase in weight gives rise to decrease in fitness. Okay. In B, this B or for that matter C, this is much stronger. So it says that even for small changes in weight initially, there is a huge drop in the fitness of the person concerned, but beyond a certain weight you have a saturation. Okay. So clearly you can see that depending on the nature of the data, you might see these two curves can be linearly correlated, or for these two curves this relationship in non-linear, that is with linear increase, if your weight doubled, will your fitness also reduce by half? Okay, that is not so. So this principle is very useful for studying correlation and regression, and let us see how it is done. So how do you know whether something is positively correlated or something is negatively correlated? So let us say if I plot my x and y, if I plot x and y and I have some scatter plots like this. Okay. So I can see that on an average, if I were to draw a trend line through the middle, my trend line will look something like this. Okay. So this is an example of positive correlation. On the other hand, if my data were to look something like this, this is negatively correlation. This is negative correlation, as we saw in the case of weight and fitness. Okay. So in other cases, so let us say for example we are correlating weight with the chance of raining today. Okay. So weight of a person at 10 different days and the chance of raining, or weight of 10 different people and the chance of raining. So we can clearly see that there is expected to be no correlation between these two curves. So in that case, if I draw a line, you see that the line will almost look like either horizontal, or in some other case it might look almost like this, that where the line is completely vertical. So these are cases where there is no correlation between x and y. Okay. So the mathematical basis for calculating correlation and regression, so what you have, so you have this, so let us just say again, in the case let us say x equal to y, you have a function which is x equal to y, we know it will be a 45-degree line passing through the origin. This is a case, you will come up with something called a correlation coefficient, which will come out to be 1. Okay. So in other words, they are fully correlated. Any increase in x will give you the equal increase in y. On the other hand, let us say you have a complete opposite slope, and this is the case where let us say y is equal to, so in this case your correlation coefficient is going to be close to value of -1, versus when there is no correlation, when you have data like this, here your correlation coefficient will give a value of 0. Okay. Now how do you define correlation coefficient mathematically? The mathematical definition of correlation coefficient is typically written as rho, is represented by rho. Correlation coefficient is nothing but defined by s x y by Sx into Sy. Okay. So, where Sx, this is standard deviation of x, standard deviation of y, and this Sxy is called the covariance of x and y. Okay. Covariance is defined by Sxy is equal to summation of xi minus x bar into yi minus y bar whole divided by n minus 1. Okay. So, let us, I can expand this further. So, I can expand this to summation of xi yi minus xi y bar minus x bar yi plus x bar y bar by n minus 1. Okay. So, I know, so my Sxy equal to summation xi yi minus y bar I can take out summation xi minus x bar I can take out summation yi plus x bar y bar summation 1 I equal to 1 to n by n minus 1. Okay. So, I can rewrite this as summation xi yi. So, summation xi is nothing but n times x bar. So, I can write this as n x bar y bar minus, similarly here it will be n x bar y bar plus n x bar y bar by n minus 1. This gives me to the formula that Sxy is summation xi yi minus n x bar y bar by n minus 1. Okay. So, this is the definition of covariance. Now, let us generate two vectors. Okay. So, let us see what kind of covariance we get, what is the value of standard deviation and what is the final correlation coefficient for some distributions. Let us take one particular example where we think that they are positively correlated. Okay. Let us assume that I have the following four values of x, and so I can calculate what is the value of x bar. X bar is equal to 2.5, y bar equal to 3.5. Okay. I can find out. So, let us open Art Studio. Okay. Let me enter. So, let us open Art Studio and let me enter xx is equal to C of 1 2 3 4. Okay. Yy is equal to C of 2 3 4 5. Okay. I can plot xx comma yy, and this is how my plot looks like. You can clearly see that there is a very linear correlation between xx and yy. Okay. So, I want to find out what is the value of Sxy. Okay. So, I can find out. So, I know that Sxy is equal to summation xi yi minus n x bar y bar by n minus 1. So, I have n is equal to 4 in this case. So, let us calculate the value of Sx. So, I can write down here itself, I can write down Sd of xx, Sd of yy, same thing. So, I can define zz equal to, I can define zz equal to, let us say Sd equal to xx star yy. So, I can find out what is the value of zz, which is nothing but summation xy. So, what I have calculated is summation xy, then I can add up. If I do sum of zz, I get the complete value which is 40. Okay. So, I can see that summation xy is coming out to be a value of 40. Okay. I know standard deviation of x is equal to standard deviation of x equal to 1.29, and Sd of both x and Sd of y is equal to 1.29. Okay. So, now let us calculate. So, I know n is equal to 4. Okay. So, sum of zz minus x bar is okay. So, minus n is 4 star x bar which is 2.5 star y bar which is 3.5 gives me a value of 5. Okay. So, I can do Sxy. So, I can get the value of Sxy. So, I got summation xy is equal to 40. I got, so Sxy is equal to summation xy minus n x bar y bar. So, I have calculated x bar is equal to 2.5, y bar equal to 3.5, n is equal to 4. So, I can calculate the value of Sxy is equal to 40 minus 4 into 2.5 into 3.5 by n minus 1 is equal to 3 is equal to 40 minus 35 by 3 equal to 5 by 3. Okay. So, and I know what is standard deviation of Sx. Okay. So, if I do Sx y, okay, so my correlation coefficient is going to be 5 by 1.29 star 1.29 . Okay. So, you can accordingly use and find out what is the correlation coefficient of rho. Okay. So, determine the formula and use to find out the correlation coefficient of y. Okay. Now, let us say one thing. So, my correlation coefficient rho is defined by Sxy by Sx into Sy. Okay. So, in this case, so my Sxy, so what is the minimum value of rho possible and what is the maximum value of rho possible? So, we thought that we reasoned that this value should be between minus 1 and 1. Okay. So, let us see if that is true. So, let us assume y as let us say Cx in this case where C is positive. Okay. Let us assume, so we assume a very strong correlation. In fact, we can also assume A plus Cx to make it more general. Okay. If we assume as y is equal to A plus Cx, then my Sxy is defined as summation of x minus x bar into y minus y bar by n minus 1, right. So, I know my y bar has to be A plus Cx bar. From previous classes we had derived this equation. So, y minus y bar is nothing but C of x minus x bar. So, this implies y minus y bar is C of x minus x bar. Okay. So, if this is true, I can compute the value of Sxy as summation of x minus x bar. So, I can take C out whole square by n minus 1. Cxy is this. Now, Sx is root of summation x minus x bar whole square by n minus 1 root of this, and Sy is equal to root of summation y minus y bar whole square by n minus 1. Okay. So, Sx into Sy will give me, so I can take out root of n minus 1, I can take out n minus 1 common into root of summation x minus x bar whole square into summation y minus y bar whole square. Okay. If this was true, then I again know y is equal to A plus Cx. So, my Sx into Xy will be 1 by n minus 1 into root of summation x minus x bar whole square into summation. So, y is A plus Cx. So, again I know y bar is equal to a plus c x bar. So, y minus y bar is equal to c of x minus x bar. Okay. So, I can put my c outside. So, c square into x minus x bar whole square. Okay. So, under root I can take it out is equal to summation x minus x bar whole square by n minus 1 into root of c square. Okay. So, this is what I have. So, in the I can write it as summation of x minus x bar whole square into n minus 1 into mod of c. Okay. So, if I do this, then my sxy, so my rho is defined as sxy by sx into sy, which is going to be is equal to c into summation of x minus x bar whole square by n minus 1 divided by summation. So, mod c summation x minus x bar whole square by n minus 1 is equal to c by mod c. Okay. So, when you see is when c is positive. So, when c is positive, so I can clearly see rho is going to be 1. So, if let us say c is 5, then 5 by mod 5 is simply equal to 1. When c is negative, rho is going to be let us say example is minus 5 by 5 equal to minus 1. This tells you that your c your rho correlation coefficient is bounded within the following limits. Okay. Rho is bounded between minus 1 and plus 1. Okay. So, this is the value of correlation coefficient. So, minimum correlation coefficient when they are anti correlated, that means x is increasing, y is decreasing, or the reverse way, x is decreasing, y is increasing. When there is complete anti correlation, you will get a value of rho which is minus 1. When they are perfectly in sync, that is x increases, y increases at the exact same rate, you would get a value of rho is equal to 1. So, when there is some association, but it need not be fully strongly associated, you might get a positive correlation or a negative correlation, but the value would be like let us say 0.2 or minus 0.2 depending on the extent of correlation. Okay. So, now let us say, so let us take another example and and do this calculation ourselves. Okay. So, let us take an example where x and y are not particularly correlated. Let us say if I take this point, this point, this point and this point. Okay. So, let us say y11, x is 2, y is 5, x is 3, y is 1, x is 4, y is 5. Okay. Let us do the following exercise. Okay. So, my x bar is going to be 2.5 as before, y bar is going to be 3. Okay. So, let us find out the standard deviation Sx. So, if I know the value of x minus x bar whole square 1, 2, 3, 4. So, it is 2 square, 1 square, 1 square, 2 square. So, Sx should give me a value of root of 4 plus 1 plus 1 plus 4 by n minus 1, which is 3, is equal to root of 5 plus 5, 10 by 3. Okay. Sx is root of 10 by 3. Okay. Sx is root of 10 by 3. I can do the same thing for y, summation y minus y bar whole square. I have 1, 5, 1, 5. Okay. So, y bar is 3, I know y bar equal to 3, 2 square, 2 square, 2 square, 2 square. So, Sy should be root of 4 into 4 by 3, solo by 3. Okay. So, we have Sx is equal to root of 10 by 3, Sy is equal to root of 10 by 3. Now we want to find out Sxy. Okay. So let us take another piece of page. Okay. So we have x, we have y, 1, 2, 3, 4, 1, 5, 1, 5, x bar. So 1 minus 2.5 into 1 minus 3, okay, 2 minus 2.5 into 5 minus 3, 3 minus 2.5 into 1 minus 3, 4 minus 2.5 into 5 minus 3. You can find out this value. So this is 2, all of them are 2, minus 2, 1.5, this is 1.5 into 3 minus into minus is plus, this value is dui minus 1, this value is 0.5, 1.5 into 2, 3. Okay. So I can calculate the summation. So Sxy will be summation of this, which is 6 minus 2 is 4 by 3. Okay. So my rho is nothing but 4 by 3 by, so this is 16 by 3, root of 10 by 3 into root of 16 by 3. So I see, so my 3 will go is 4 by 4 into root 10 is equal to 1 by root 10. Okay. So I will get a value which is root of 3 is 1/3, roughly 1/3. So you see that this is still positively correlated as per this calculation, or it is much lesser than 1, but it is still positive. Okay. So in this class we discussed about correlation coefficient and how you can make use of R to calculate these individual metrics and even calculate the correlation coefficient. In the next class we will again take few more examples of correlation and then go to the next step of how to do regression and fitting. With that I end here and I look forward to meeting you in the next lecture. Thank you.